students, our topic for today is differentiability of a function. In order to understand the differentiability of a function, you need to know the definition of the derivative, which is f dash x equals to h, limit h tending to 0, f of x plus h minus fx divided by h, where h is a slight increment in x. I think you know this definition. Okay, we are going to use this. Now, in order to check the differentiability of a function at the point x equal to a, for example, what we need to do is we need to find the left-hand derivative of the function at that point, and we'll need to find the right-hand derivative of the function at that particular point. Okay, now how we are going to do it, let us see. The left-hand derivative of the function is denoted by L of f dash a or f dash of a minus. Got that? Now, in the definition of the derivative, all you need to do is instead of limit h tending to 0, you're going to write limit h tending to 0 minus. Okay? And wherever there is x, put a. Clear? Wherever there is x in the definition, put a. So you'll have f of a plus h minus f of a divided by h. Simple, calculate, you will get your left-hand derivative. What we are doing over here is we are checking to find the values of the left-hand derivative at the point x equal to a, right? But when the value of the function is very, very close to a but not equal to a. Got it? Okay. Similarly, next we are going to find right-hand derivative. Can be denoted as plus also. The right-hand derivative is calculated as limit h tending to o plus f of a plus h minus f a divided by h. This is the definition of your right-hand derivative. Okay. If your point given is x equal to a, you'll replace all the x values by a. If your point given is x equal to 2, replace all the x values by 2 and so on. Got that? When you are finding out the right-hand derivative, then you are finding out the derivative of the function at a point very, very close to a and slightly greater than a. Got that? Okay. Now, once your left-hand derivative and right-hand derivative are found out and the values are coming equal, like this. If your left-hand derivative is equal to your right-hand derivative, it means that your function is differentiable at the point x equal to a. Okay, or in other words, for a function to be differentiable at a point, the left-hand derivative must be equal to the right-hand derivative. This is the condition for differentiability of a function. Got it? Okay. Now, there is a relation between continuity and differentiability of a function. The relation is that if a function fx is differentiable at x equal to a, then the function must be continuous at x equal to a. In simple words, we can understand like this. If you get a differentiable function, you automatically understand the function is also continuous. You don't have to check for continuity. If the function is differentiable, it is understood that the function is also continuous. Okay? Why? Because every differentiable function is continuous according to this theorem. Got it? Okay, let us check some examples. Okay, this is the first one. Your question says, examine the function f for continuity and differentiability at x equal to 0, where fx equal to 1 minus x square, where x is less than or equal to 0, and fx equal to 1 plus x square when x is greater than 0. Now, you have to check for continuity and differentiability of the function at the point x equal to 0. So, let us first check for continuity. Okay, now see. For checking the continuity of the function, you know that you will have to calculate the value of the left-hand limit and the right-hand limit. So, value of left-hand limit, limit x tending to 0 minus fx equals to limit x tending to 0 minus. 0 minus means the value of x lesser than 0. For x less than 0, your fx is 1 minus x square. So, that is why in place of fx, we are going to write 1 minus x square. Got that? Equals to, put the value of limit 1 minus 0 square, which is equal to 1. Your left-hand limit is 1. Now find your right-hand limit. Limit x tending to 0 plus fx. That is limit x tending to 0 plus means values of x greater than 0. For x greater than 0, your fx is 1 plus x square. So in place of fx, we are writing 1 plus x square. Putting the value of the limit, you get 1 plus 0 square, which is equal to 1. Done. Now you can see the left hand limit and the right hand limit both are coming equal. So if that is the case, we are going to find f0 also. Okay, value of the function at the point x equal to 0. So f0 is at x equal to 0. Your value of the function is 1 minus x square. So at x equal to 0, your 1 minus x square is, in place of x we are going to put a 0. So it is 1 minus 0 square, which is equal to 1. Now you can clearly see all three values are equal to 1. That means your left hand limit, right hand limit and f0 all are equal. That is why your function is continuous at x equal to 0. So when we examine the continuity, we found out our function is continuous at that given point. Clear? Now let us go to differentiability of that function. Now, in order to check the differentiability, just now I told you, you'll have to find out the left hand derivative and the right hand derivative. So let us find the left hand derivative. Write down the formula that I taught you. Left hand derivative, that is L f dash. Your point is 0. You're checking at x equal to 0. So f dash over here 0 equals to limit h tending to 0 minus f of, wherever there is x, put a 0. 0 plus h minus f0 divided by h. Got that? Now, it will be equal to limit h tending to 0 minus 0 plus h is h minus f0 by h. Now, fh, when x is lesser than 0, fh will be at x less than 0, your fx will be 1 minus x square. So fh will be 1 minus h square. So putting that over here, you have fh is 1 minus h square minus f0 is 1 minus 0 square, that is 1 minus 0. Cancelling, simplifying, you got minus h square by h. So h gets cancelled. You are getting limit h tending to 0 minus of minus h. Okay, so this is limit h tending to 0 minus of minus h. Now putting the value of the limit here, you got minus 0, which is equal to 0. So my left hand derivative is 0. Similarly, calculate the right hand derivative. Put the values, put the formula. Okay, calculate fh. Now your value of x is greater, right? Greater than the 0. At x greater than 0, your fx is 1 plus x square. So obviously fh is 1 plus h square. So put the value over here. Limit h tending to 0 plus 1 plus h square minus f0 is 1 plus 0 square divided by h. Simplify, 1 plus h square minus 1 by h. Cancel, it is equal to 0. So what am I finding out? My left hand derivative and right hand derivative both are equal to 0. Correct? And so my condition for differentiability is being fulfilled. So I will write f is differentiable at x equal to 0. So this is how your sum is to be done. Okay, now there is an alternate way to solve the same particular problem. What is the alternate way? In the theorem we just discussed that if a function is differentiable, it is automatically continuous. Correct? Now the question asks you to check the continuity and differentiability of a function. What did we do? We worked out in the traditional method. Whatever was asked, we did. We calculated the continuity and then we checked for differentiability. Okay, but rather than doing that, you could use a little bit shorter method. Okay, what you can do is you can directly first find whether a function is differentiable or not. Okay. Now, when you check if the function is differentiable or not, if you find out, now in this particular question, we understand and we see that my function is coming differentiable. Now, since the function is differentiable, our theorem says that every differentiable function is continuous. Since this is there, my function is already differentiable. So I can say that yes, the function is also continuous. Correct? Since the function is differentiable, therefore it implies that the function is also continuous. So no need to find this continuity. No need to calculate this process. It automatically follows from here that the function is also continuous. So this also you can do.